Right now, as you lie here, the universe is expanding. Not slowly, not steadily. Faster than it was a second ago. Faster than it was a year ago. Faster than it was 1 billion years ago. And the strange thing, the thing that keeps physicists up at night, is that the force driving that expansion is something we cannot see, cannot measure directly, and cannot explain. We just know it is there because the universe keeps telling us it is. Every second that passes, the fabric of space stretches a little more. Galaxies that were once close enough to see are now racing away from us faster than light itself could cross the distance, not because they are moving through space, but because space between us and them is growing. There is no engine pushing them. There is no hand pulling them. Space itself is the engine, and it has been running without pause for 13.8 billion years. Tonight, we are going to follow that engine as far as physics will allow us to go. We are going to travel, together, from the edge of everything we can see, out into what lies beyond. And what lies beyond is not empty. It is not silence. It is not nothing. What lies beyond our cosmic horizon is, depending on how you look at it, either the most beautiful or the most unsettling landscape the human mind has ever tried to imagine. Scientists have been working on this for decades, and in the last few years some of the most significant results in the history of cosmology have started coming in. Results that suggest our best model of the universe, the one we have trusted for 30 years, may be incomplete. Results that suggest the force we thought was pushing the cosmos apart may be changing. Results that open up questions about what this universe is, whether it is the only one, and what, if anything, waits beyond its edge. We are going to go through all of it, slowly, carefully, without rushing. This is a long journey. There is no reason to hurry. The universe has been out there for 13.8 billion years. It will wait for us. Let us begin. Chapter 1. The wall we cannot see through. Before we can talk about what lies beyond the observable universe, we need to understand what the observable universe actually is. Because this is one of those phrases that gets used often, and understood rarely, and the difference between what it sounds like and what it actually means is exactly where the wonder lives. The observable universe is not the universe. It is a sphere of space centered on Earth, bounded not by walls or edges or any physical structure, but by time. Specifically, by the age of the universe and the speed of light. Light travels at approximately 299,792 kilometers per second. That is the fastest anything can travel through the cosmos, and the universe has existed for approximately 13.8 billion years. So the maximum distance that light from any source could have travelled to reach us is 13.8 billion light years. But here is where it gets counterintuitive, and it is worth slowing down on this because it is the foundation of everything that follows. The universe is not 13.8 billion light years across. It is 93 billion light years across at minimum. The reason for this is that space has been expanding the entire time light was travelling. When light from a distant galaxy set off toward us, billions of years ago, the galaxy was much closer than it is today. By the time that light arrives at our telescopes, the galaxy that sent it has been carried much farther away by the expansion of space. So the farthest objects whose light can reach us are now roughly 46.5 billion light years away, not 13.8 billion. The observable universe is a sphere with a radius of 46.5 billion light years and a diameter of approximately 93 billion light years. Those numbers were established through decades of careful measurements, most recently refined by the Planck satellite mission, which mapped the cosmic microwave background with extraordinary precision. They are not estimates or guesses. They are the best measurements physics can produce. Now, what is at the edge of that sphere? The edge of the observable universe is not a wall. There is no boundary you would cross, no line in space where things simply stop. What sits at the limit of our visibility is something called the cosmic microwave background. This is the oldest light in the universe, and understanding what it is and where it came from is essential to understanding what lies beyond it. In In the first moments after the Big Bang, the universe was extraordinarily hot and dense, so hot that electrons and protons could not combine to form atoms. They existed as a dense plasma, and this plasma was opaque. Light could not travel through it. Photons were continuously absorbed and re-emitted, trapped in a kind of cosmic fog. For the first 380,000 years of the universe's existence, no light could travel freely anywhere. Then the universe cooled. As space expanded, the temperature dropped to roughly 3,000 degrees Kelvin, and something remarkable happened. Electrons slowed down enough to be captured by protons, forming the first hydrogen atoms. The plasma became a gas. The cosmic fog lifted, and for the first time light could travel freely across the universe. That moment is called recombination, and the light released at that moment has been travelling ever since. It has been travelling for approximately 13.8 billion years. It has been cooling the entire time, stretched by the expansion of space from visible light into microwaves, and it reaches us today from every direction in the sky, a faint glow of microwaves at a temperature of 2.725 degrees above absolute zero. This is the cosmic microwave background. The Planck satellite, launched by the European Space Agency in 2009, mapped this radiation with the finest resolution ever achieved. The WMAP satellite, launched by NASA in 2001, mapped it before that. Every direction we look, the CMB is there, nearly perfectly uniform, nearly perfectly smooth, with tiny temperature fluctuations of 1 part in 100,000. Variations so small they would be invisible to your eye, but so important that without them, no galaxy, no star, no planet, no human being would ever have existed. Those tiny fluctuations were the seeds of everything. But here is what the CMB also tells us, and this is what matters most for tonight's journey. The cosmic microwave background tells us the shape of space. Physicists used data from WMAP and Planck to measure the angles of the largest triangle it is possible to construct in the cosmos. One corner of that triangle is here, at Earth. The other two corners are located at the surface of last scattering, the shell from which the CMB was emitted, roughly 46 billion light years away in opposite directions. In flat space, the angles of any triangle add up to exactly 180 degrees. In positively curved space, like the surface of a sphere, they add up to more than 180. In negatively curved space like a saddle, they add up to less. The measurements showed that the angles add up to 180 degrees, to within the precision of the instruments, to within roughly 1%, the universe is flat. Not slightly curved, not gently warped. Flat. And this result is held through every subsequent measurement. Planck confirmed it. WMAP confirmed it. It is one of the most robustly established facts in modern cosmology, and a flat universe has a consequence so large it is difficult to hold in your mind. In Euclidean geometry, flat space is infinite. If the geometry of the universe is truly flat, if there is no curvature hiding just below the threshold of our measurement, then space does not curve back on itself. It does not loop. It does not end. It extends in every direction without limit, forever. Beyond the edge of our observable universe, the universe continues. The same laws of physics apply. The same kinds of galaxies and stars and planets exist. The same dark matter holds structures together. The same dark energy pushes them apart. The region beyond our cosmic horizon is not a different universe. It is the same universe. We simply cannot see it yet, because its light has not had time to reach us. Think of it this way. If you are standing in a field on a dark, foggy night, you can see perhaps 100 meters in any direction. But the fog does not mean the world ends at 100 meters. The world continues beyond the fog. The cities and mountains and oceans beyond your visibility are still there. You are simply limited by what you can detect. Our cosmic horizon is humanity's fog. The universe beyond it is still there. The laws of physics still hold. Stars are still burning, galaxies are still spinning, and the story continues in every direction we cannot see. This is the first and simplest answer to the question of what lies beyond the observable universe. More universe, the same universe, extending in all directions, probably forever filled with the same structures and the same physics that fill the portion we can observe. But this answer, as satisfying as it is, immediately raises a deeper question. If the universe extends infinitely in all directions, if it is filled with galaxies and stars distributed according to the same patterns we observe here, then what are the implications of that infinity? What does it mean, mathematically and physically, to have infinite space? The answer to that question is where things begin to get genuinely strange, and it is where we are going next. But first, let us sit with what we have established. The observable universe is 93 billion light years across. Its edge is defined by time, not by space. The cosmic microwave background is the oldest light we can detect, a record of the universe at 380,000 years old. And the measurements of that background radiation tell us that space, as far as we can determine, is flat. Flat and, if the simplest interpretation holds, infinite. The universe has been here for 13.8 billion years, and it appears to have no edge. There is no wall. There is no boundary. There is only more. Take a breath. Let that settle. Because in the next chapter we're going to follow what infinity actually means, and the place it leads us is somewhere no one expected. Chapter 2. More of the same forever. If the universe is infinite, then it contains an infinite amount of matter, an infinite number of galaxies, an infinite number of stars, an infinite number of planets, and on some of those planets, in the right conditions, an infinite number of possible arrangements of atoms. Here is where the mathematics becomes genuinely disorienting. Quantum mechanics, the science of the very small, places a fundamental limit on how many different ways matter can be arranged within a given volume of space. This is because information in the universe is not continuous, it is quantized. There are a finite number of quantum states available to any given system, and those states are determined by the energy content and size of the system. For a volume of space the size of our observable universe, the number of possible quantum states, and therefore the number of possible distinct configurations of matter, is enormous but finite. It is approximately 10 to the power of 10 to the power of 118. That number, written out, would have more digits than there are atoms in the observable universe. It is, for all practical purposes, incomprehensibly large, but it is not infinite. And this is where infinity does something that feels almost like a logical paradox, but is in fact completely mathematically sound. If the universe is infinite, and if matter is distributed roughly uniformly throughout it, which is what we observe in the portion we can see, then somewhere beyond our cosmic horizon, every possible configuration of matter must eventually repeat. Not approximately repeat, exactly repeat, because there are only finitely many ways matter can be arranged in a given volume, and there are infinitely many such volumes in an infinite universe. Every arrangement must recur an infinite number of times. The physicist Max Tegmark, a cosmologist at MIT, has calculated the approximate distance to the nearest region of space with a configuration identical to our other observable universe. His estimate is approximately 10 to the power of 10 to the power of 118 meters. That is not a distance that any spacecraft could ever cross. It is not a distance that light could cross in the current age of the universe or in any conceivable future. It is so far beyond what is physically accessible that it might as well be another kind of existence entirely. But the mathematics says it is there. And if it is there, then there is a region of space, right now, impossibly far away, where the arrangement of every atom is identical to the arrangement in our observable universe, where a planet identical to Earth exists, where every person you know exists in a configuration identical to the one they occupy tonight, where someone identical to you is lying in a space identical to this one, thinking these identical thoughts, listening to this identical voice describing this identical situation. The laws of physics, taken seriously, produce this conclusion. Now, before this becomes distressing, it is worth noting what this actually means and what it does not mean. It does not mean those distant regions are in any sense connected to us. There is no way to communicate with them, no way to travel to them. They are separated from us not just by distance, but by the expansion of space, which will carry them ever farther away. They are, for every practical purpose, irrelevant to anything that happens here. But they are not nothing. They are real, in whatever sense the word real applies to regions of space that can never interact with us. And the fact that infinite space produces infinite repetition is a mathematical certainty, not a philosophical speculation. If the universe is truly flat and truly infinite, this is the baseline, the simplest answer to what lies beyond our cosmic horizon. More universe, the same galaxies, the same physics, the same arrangements of matter, recurring endlessly in an infinite sea of space. But the flat infinite universe, as strange as it already is, cannot answer a deeper set of questions, and those questions are the ones that drove physicists towards something more radical. The flat infinite universe tells you what lies beyond the horizon. It does not tell you why the universe has the properties it has, why the speed of light is what it is, why the electron has the mass it has, why the cosmological constant, the number that governs the expansion of space, has the tiny precise value it has rather than being billions of times larger, which would have torn the universe apart before any galaxy could form, or billions of times smaller, which would have caused everything to collapse. Why? In a universe governed by equations that treat matter and antimatter symmetrically, we find ourselves in a cosmos made almost entirely of matter. These are not questions the flat infinite universe can answer. For those you need to go somewhere more unsettling. For those you need inflation. Chapter 2, continued, the numbers we cannot hold. Before we move on from the question of infinite space, it is worth sitting a little longer with what infinity actually does to mathematics. Because the concept of infinity is one of those words that the human brain uses comfortably in conversation but cannot genuinely hold as a concept. We say the word. We understand what it is supposed to mean. But no human nervous system has ever actually felt the weight of it. And the reason this matters tonight is that what lies beyond our observable universe is not a place we can imagine visiting. It is a structure we can only approach through mathematics. And the mathematics of infinity is, even in its simplest forms, genuinely strange. The mathematician Georg Cantor spent much of the late 19th century working up the properties of infinite sets, and he discovered something that troubled him deeply and that has troubled mathematicians ever since. There is more than one size of infinity. The set of all whole numbers, the counting numbers that go 1, 2, 3, 4 and so on without end, is infinite. The set of all even numbers is also infinite, and yet there are exactly as many even numbers as there are whole numbers, because you can pair them up 1 to 1, every whole number matched to its double, without anything left over. Infinity does not follow the same arithmetic as ordinary numbers. Cantor showed that the set of all real numbers, which includes not just whole numbers, but all the fractions and irrational numbers in between, is a strictly larger infinity than the set of whole numbers. There are more real numbers between 0 and 1 than there are whole numbers in the entire counting sequence. This was not a metaphor. It was a rigorous mathematical proof, and it meant that infinity was not a single thing but a hierarchy of things, each one larger than the last without end. The universe, if it is infinite, contains infinitely many distinct regions of space, and in that infinite space the claim that every possible arrangement of matter recurs is not poetry. It is a consequence of combinatorics. If there are a finite number of possible quantum configurations in a volume the size of our observable universe, and there are infinitely many such volumes in an infinite universe, then every configuration must appear infinitely often. The logic is as simple and as unavoidable as any in mathematics. What this means for what lies beyond our horizon is that the answer at the mathematical level is more of this, more of the particular configuration of matter and energy and physical laws that we inhabit, more of it in every direction, without limit, until the pattern changes in ways too distant to influence us, and then repeats, and changes again and repeats. More universe, the same universe, extending everywhere and infinite in every direction we cannot see. This is the most likely answer to what lies beyond the edge of everything we can observe, and there is something genuinely stabilizing about it if you let it settle in. The universe is not doing something different out there, it is simply continuing. The same stars, the same dark matter halos, the same cosmic web of filaments and voids, extending in every direction, identical in its general character to what we observe here. The horizon is not a wall, it is a window, and through the window the view is the same as it is on our side. But the flat, infinite universe, as grounding as it is, cannot explain why the universe has the specific properties it has, why the constants of physics are what they are, why the universe exists in the particular configuration that allows us to exist inside it. For that, we need to follow the physics backward in time to the first fraction of a second after the Big Bang and ask what happened there. What force, what mechanism shaped the cosmos into the thing we observe? The answer is inflation. And inflation, taken seriously, leads somewhere remarkable. Chapter 3. The Inflationary Storm. How Universes Are Born. In the autumn of 1979, a physicist named Alan Guth was working late at the Stanford Linear Accelerator Center. He was a postdoctoral researcher, recently arrived, trying to solve a specific problem in the standard model of the Big Bang. He had been thinking about a class of exotic particles called magnetic monopoles, which the theory predicted should exist in large quantities, but which no one had ever found. He was trying to understand why. His diary for that night has been quoted many times since. He wrote 2 words: spectacular realization. What Guth had worked out in a single sleepless night would become one of the most important ideas in the history of cosmology. He called it inflation. The standard Big Bang model had several problems in 1979. The magnetic monopole problem was one, but there were others. The horizon problem. How did regions of space on opposite sides of the sky, separated by billions of light years, end up with nearly identical temperatures? They could never have been in contact with each other in the standard model. There was not enough time. And yet the cosmic microwave background shows them to be identical to 1 part in 100,000. How? The flatness problem was another. The equations of general relativity show that any small deviation from perfect flatness in the early universe would grow rapidly over time. For the universe to be as close to flat as we observe it today, it would have had to be extraordinarily, almost impossibly flat in its earliest moments. Why? Guth's answer was elegant in the way that the best physical theories always are. He proposed that in the first fraction of a second after the Big Bang, before any of the familiar physics we know had time to operate, the universe underwent a period of extraordinarily rapid expansion. Not the gradual expansion we observe today, something far more violent. A period during which space doubled in size perhaps 100 times or more, in an interval far shorter than any unit of time we use in daily life. A billionth of a trillionth of a trillionth of a second. During this period, a tiny region of space, smaller than a proton, expanded to a size larger than the observable universe today. Everything that exists in the cosmos we can see descended from that single microscopic patch. The horizon problem dissolves. Every region we observe descends from a region so small that it was before inflation in complete thermal contact with itself. It reached equilibrium before inflation stretched it to cosmic scales. That is why the sky looks the same in all directions. The flatness problem dissolves. Inflation stretches space so dramatically that any initial curvature becomes undetectable. A sphere inflated by a factor of 10 to the 30th power appears flat to any observer on its surface. This is why the universe looks flat. Not because it is perfectly flat, but because inflation stretched whatever curvature it had to scales far beyond what we can observe. And the magnetic monopoles? Diluted to 1 per Hubble volume, effectively to 0. That is why we have never found one. Gough's theory was a breakthrough, but it raised a question no one had initially considered. What caused inflation to stop? In 1982 and 1983, Andrei Linde at Moscow's Lebedev Physical Institute, and separately Paul Steinhardt and Andreas Albrecht at the University of Pennsylvania, proposed refinements to Gough's model. And in 1986, Linde, now at Stanford, developed what he called chaotic inflation. And it was in the mathematics of chaotic inflation that something unexpected appeared. Inflation, it turned out, does not stop everywhere at once. The quantum field driving inflation, which physicists call the inflaton field, behaves differently in different regions of space. In most places, quantum fluctuations keep the field high enough to sustain continued inflation. Occasionally, in isolated pockets, the field falls low enough that inflation ends and a hot, dense region forms. A region that, from inside, looks exactly like a Big Bang. A region that expands and cools and fills with matter and energy, and eventually, perhaps, with stars and planets. Our universe is one of those pockets. Around and between such pockets, inflation continues forever. The volume of space undergoing inflation grows faster than the pockets carved out of it. New pocket universes form constantly, and this process, according to Linde and Gough and Alexander Vilenkin and the many physicists who have worked on this in the decades since, has no natural end. It is eternal. Alan Guth, in a 2007 paper titled Eternal Inflation and Its Implications, put it plainly. He wrote that almost all inflationary models lead naturally to a situation in which inflation continues forever, producing an infinite sequence of pocket universes. And he made an observation that once you hear it, you cannot unhear. He wrote that inflationary cosmology suggests that even though the observed universe is incredibly large, it is only an infinitesimal fraction of the entire universe, not a small fraction, an infinitesimal one. Our entire observable universe, with its 93 billion light-year diameter, its hundreds of billions of galaxies, its trillions of stars, its countless planets and moons and asteroids and clouds of gas, all of it is a rounding error, a speck in the inflationary sea. And in that sea, new universes are forming right now. This is not a metaphor. This is not a story physicists tell to make cosmology more exciting. This is the direct prediction of a theory that was developed to solve specific, measurable problems, and that has since been confirmed in its essential features by satellite measurements of the cosmic microwave background. The Planck satellite's maps of the CMB are consistent with inflation. The fluctuation spectrum, the statistical pattern of hot and cold spots in the CMB, matches what inflation predicts. Inflation is not proven beyond any possible doubt. No theory in physics ever is. But it is the leading framework in cosmology for very good reasons. And inflation predicts other universes, not in some vague speculative sense, in the same sense that the equations of general relativity predicted black holes before anyone had observed one, in the same sense that quantum mechanics predicted the Higgs boson before the Large Hadron Collider confirmed it. Eternal inflation follows mathematically from the same framework that explains the flatness of the universe, the uniformity of the CMB, and the absence of magnetic monopolies. Chapter 3. Continued. What the James Webb Space Telescope is telling us. Before we move from inflation to the string landscape, it is worth pausing on something that has happened in the last few years that bears directly on our understanding of the early universe, because we are not just theorizing about what happened in the first moments after the Big Bang. We are actively observing the aftermath with the most powerful telescope ever built. The James Webb Space Telescope was launched on December the 25th, 2021. It is positioned at a location in space called the second Lagrange point, approximately 1.5 million kilometers from Earth in the direction away from the Sun. From there, it observes the universe in infrared light, wavelengths longer than visible light, which are essential for seeing the most distant galaxies because the expansion of the universe has stretched their emitted light from ultraviolet or visible wavelengths all the way into the infrared. What Webb has found in its first few years of operation has, in some respects, surprised astronomers considerably. The standard cosmological model, supported by inflation, predicts how the first galaxies formed. After the Big Bang, matter was distributed almost uniformly, with tiny quantum fluctuations of 1 part in 100,000. Gravity amplified those fluctuations. Over hundreds of millions of years, dense regions attracted more matter, while underdense regions became voids. The first galaxies should have been small, irregular, and relatively few in number at early cosmic times. They should have grown into larger, more regular structures over billions of years, through mergers and accretion of surrounding gas. Webb has found galaxies far earlier in cosmic history than expected, and some of them are surprisingly massive and surprisingly regular for their age. Galaxy JADES-GS-Z 14-0, confirmed in 2024 to have a redshift of approximately 14.32, exists as we see it when the universe was only about 290 million years old, less than 2% of the universe's current age. It is not a tiny irregular proto-galaxy. It is substantial, with a diameter of roughly 1,600 light-years and a mass of several 100 million times the mass of the Sun. It is already producing stars at a rate far higher than the models predicted for such an early time. This galaxy is not alone. Webb has found multiple examples of unexpectedly massive, unexpectedly structured galaxies at very high redshifts. Not enough to falsify the standard model outright, but enough to push on it. Enough to require theorists to reconsider their assumptions about how quickly star formation and galaxy assembly can proceed in the early universe. Some researchers have proposed that the early universe contained more dark matter in compact forms that seeded galaxy formation, more efficiently than the standard picture assumes. Others have proposed modifications to the initial conditions of inflation itself, suggesting that the fluctuation spectrum produced by inflation was not perfectly smooth but contained additional structure at small scales that accelerated early galaxy formation. Still others are examining whether the standard assumptions about when the first stars ionized the intergalactic medium need revision. None of these proposals has been confirmed. This is science at its most active. The data is new, the models are being tested, the understanding is evolving. But what Webb is doing, without ambiguity, is giving us direct visual access to cosmic epochs that were previously inaccessible. We can now see galaxies from when the universe was only a few % of its current age. We can observe the conditions that existed a few 100 million years after the Big Bang. We can compare what we see to what the models predict. And in doing so, we are answering partially one of the oldest questions in cosmology. What was the universe like when it was young? What were the first structures? What were the conditions from which everything we observe today descended? The answer Webb is providing is more complex than we expected, more varied, more structured at earlier times than the simplest versions of the standard model predicted. And this complexity, this richness at early times, connects back to the question of what lies beyond our horizon. Because if the early universe was more active, more structured, more rapidly evolving than we assumed, then the same physics that produced the early galaxies Webb can see was operating across the entire universe, not just the portion we observe. Whatever surprises exist in the early history of our observable universe exist equally in the early history of the universe beyond our horizon. The first galaxies in distant, unobservable regions of the cosmos faced the same conditions. The same inflation produced the same fluctuation spectrum. The same dark matter halos assembled under the same gravity. The same physics of star formation and galaxy assembly operated across all of space simultaneously. What Webb is showing us is not just the history of our little corner of the cosmos, it is a window into a universal history. The early universe we observe is a sample of the early universe everywhere, and understanding it better here refines our understanding of it everywhere, including in the infinite regions we will never see. This is the peculiar power of observational cosmology. You can only observe from one vantage point. You can only see within one cosmic horizon, but the physics is universal. What you learn here applies everywhere, the laws that govern the galaxies. Webb observes at redshift 14 are the laws that govern galaxies in every direction, including directions no telescope will ever point. The universe beyond our horizon is not a mystery in the sense of being governed by different rules. It is a mystery only in the sense of being unreachable. The physics we understand here is the physics that applies there, and as our understanding of the physics deepens, our picture of what lies beyond becomes, in a meaningful sense, sharper. Webb is sharpening it right now. Every observation it makes, every galaxy it resolves, every spectrum it records, adds to our understanding of how the universe works. And that understanding is not confined to our horizon. It radiates outward, conceptually, across all of space. In a universe where observation is limited to a finite sphere, theory is the only vehicle that can carry understanding beyond that sphere. And the theory we are building, informed by Webb's observations of the early universe and DES-Junger's measurements of dark energy and Planck's maps of the CMB, is the most detailed and most carefully tested description of reality that any civilization has ever constructed. It is still incomplete. The Hubble tension remains. The dark energy evolution signal is unconfirmed. The early massive galaxies Webb has found are not yet fully explained. But the incompleteness is not a failure, it is a frontier, and frontiers are where the best science happens. We are at the frontier right now, standing at the edge of what we know, looking outward at the vast territory of what we do not know, and building instruments to explore it. That is where we always are in science, and it is a good place to be. Now, the pocket universes beyond our horizon, if they exist, were forged in the same inflationary event that forged ours. The early galaxies in those universes face the same physics that the early galaxies Webb observes faced. The same dark energy is accelerating the expansion of space in those universes, or perhaps not, if dark energy is evolving and each pocket universe settles into a different vacuum state. The picture is complicated, but it is not chaotic. It is governed by mathematics. And mathematics, followed carefully, leads to specific predictions about what exists beyond our horizon, predictions that in some cases are already being tested. Now, here is the question that naturally follows. If other pocket universes exist, what are they like? And here the story deepens considerably. Each pocket universe forms when inflation ends in a particular region, and the inflaton field settles into a stable low-energy state. But quantum mechanics allows for many different stable states. In fact, when you combine inflationary cosmology with string theory, the theoretical framework that attempts to unify quantum mechanics with gravity, the number of possible stable states is staggering. It is approximately 10 to the power of 500. That number deserves a moment of contemplation. 10 to the power of 500 is not just a large number. It is a number so vast that it makes the number of atoms in the observable universe, which is approximately 10 to the power of 80, look like a rounding error in comparison. If you tried to write it out, the number of digits you would need would itself exceed the number of atoms in the observable universe by a factor greater than the number of atoms in the observable universe. Each of these 10 to the 500 possible stable states corresponds to a different possible universe, a universe with a different value of the cosmological constant, a different mass for the electron, a different strength of the electromagnetic force, a different number of spatial dimensions, different particles, different interactions, different possibilities for complexity. Most of these universes would be empty. In most configurations, the constants of physics would prevent atoms from forming, stars from igniting, planets from cohering. The universe would consist of featureless radiation, or bare particles, or nothing at all recognizable to us. But some configurations, a small fraction of an incomprehensibly large number, would produce universes capable of complexity, capable of chemistry, capable of life. And in those universes, if life arose, observers would look at the constants of physics and ask why they have the values they do. And the answer in this picture would be, because you could not exist in a universe where they had different values. You are here because you are in one of the universes where being here is possible. This idea goes by the name of the anthropic principle, and it is one of the most debated concepts in modern physics. Some physicists find it deeply satisfying. Others find it troubling in a way that is hard to articulate. It feels like it removes the possibility of a final explanation. If the constants of nature are what they are simply because we could not exist otherwise, then there is no deeper reason to find. There is no equation from which the electron mass follows as a logical necessity. There is just selection. Steven Weinberg, who won the Nobel Prize in Physics in 1979 for his work unifying the weak nuclear force and electromagnetism, predicted in 1987 that if the multiverse exists and the cosmological constant can vary across universes, then the value of the cosmological constant in our universe should be small, but non-zero. Small enough to allow galaxy formation, but non-zero enough to be detectable. 11 years later, in 1998, astronomers discovered that the universe's expansion is accelerating. The cosmological constant, which Einstein had introduced as a blunder and discarded, turned out to be real, and its value was small, non-zero. Exactly in the range Weinberg had predicted. This is sometimes called the most successful prediction in physics that no one is comfortable with. The multiverse made a prediction. The prediction came true. And yet most physicists remain uneasy, because the multiverse cannot be directly tested. We cannot observe another universe. We cannot communicate with one. We cannot send a probe into the inflationary sea and return with samples. But perhaps we do not need to. Perhaps the other universes have already left marks on ours. And this is where, in the next chapter, we follow a specific possibility that researchers have been quietly investigating for years. But before we go there, let us pause on what we have built so far. The observable universe is 93 billion light years across, bounded by a time limit, not a wall. Beyond it, if space is flat, the same universe continues, probably forever. And inflation, the theory that explains the flatness and the uniformity we observe, predicts that our pocket of that infinite space is surrounded by a vast, perhaps infinite inflationary sea, from which new universes are constantly being born. Universes that may have different physics, different constants, different possibilities. Universes that may contain nothing at all, or universes that contain everything we cannot imagine. We are one bubble in an eternal foam, and somewhere out there, other bubbles may be forming right now. Chapter 4. The Dark Energy Revelation. What 2025 changed. In the spring of 2025, a collaboration of more than 900 researchers from more than 70 institutions around the world released a set of results that quietly shook the foundations of modern cosmology. The instrument responsible was called DESI, the Dark Energy Spectroscopic Instrument, and what it found may be the most important astronomical measurement made in the last 25 years. To understand what DESI found, you need to understand what dark energy is and why it matters. In the late 1990s, two independent teams of astronomers were doing something that sounds straightforward, but requires extraordinary care. They were measuring the brightness of supernovae in distant galaxies. Type 1. A supernovae are a particular class of stellar explosion that always produces roughly the same peak brightness, making them useful as what astronomers call standard candles. If you know how bright something actually is and you measure how bright it appears, you can calculate how far away it is. And if you know how far away it is, combined with how fast the universe is expanding at that distance, you can piece together the history of cosmic expansion. What the two teams found was not what anyone expected. The supernovae were dimmer than they should have been, not a little dimmer, consistently, significantly dimmer. The only way to explain this was that the universe's expansion had been accelerating over the past several billion years, not slowing down as matter's gravity should have caused it to do, speeding up. Something was pushing space apart, something that did not dilute as the universe expanded, something that, as space grew with it, filling every new cubic meter of space with the same energy density as before. The teams called it dark energy. The Nobel Committee called it worthy of the 2011 Nobel Prize in Physics. And for nearly 3 decades, our best model of the universe has incorporated dark energy as a cosmological constant, a fixed amount of energy per unit volume of space, unchanging across time. Einstein had originally introduced this constant, which he called lambda, into his equations of general relativity in 1917, attempting to produce a static universe. When Edwin Hubble discovered that the universe was expanding, Einstein abandoned lambda, reportedly calling it his greatest blunder. The irony is that Einstein's blunder turned out to be real. It just was not doing what he thought it was doing. Lambda, in our standard cosmological model, has a specific value, a very small value, so small that it took a century to measure it, but non-zero, and as long as lambda stays constant, the future of the universe is determined. Space will continue to expand, accelerating forever. The galaxies we can see today will gradually recede beyond our cosmic horizon. New stars will form more slowly as gas disperses. Eventually the stars will exhaust their fuel. The universe will grow cold and dark. This scenario is called the Big Freeze, and in the standard model, it is the certain fate of everything. But in March of 2025, DESI released its second major dataset, and the data told a different story. DESI is mounted on the Nicholas U. Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. It is unlike any previous astronomical instrument in one crucial respect. It can observe 5,000 galaxies simultaneously, using 5,000 optical fibers controlled by robotic actuators that constantly reposition to track different objects. By the time its survey concludes, DESI will have measured the spectra of roughly 50 million galaxies and quasars. Its second data release alone included nearly 15 million objects, spanning 11 billion years of cosmic history. From these spectra, DESI can measure something called baryon acoustic oscillations. In the early universe, before recombination, the hot plasma was not perfectly uniform. Sound waves, pressure waves, travelled through it at roughly half the speed of light. When recombination occurred and the plasma became transparent, those sound waves froze. They left an imprint in the distribution of matter, a preferred scale, a distance at which galaxies are slightly more likely to cluster together than at random. This scale is known precisely from the CMB measurements. It is approximately 500 million light-years. By measuring how this preferred scale has changed across cosmic time, DESI can map the history of expansion with extraordinary precision. And what the map showed, when combined with CMB data, supernova measurements, and weak gravitational lensing, was that dark energy does not look like a constant. Alexei Luthod-Harnett, co-spokesperson for DESI and a professor at UC Santa Cruz, said in March of 2025 that what they are seeing is deeply intriguing, that it is exciting to think they may be on the cusp of a major discovery about the fundamental nature of the universe. Will Percival, the other co-spokesperson, a professor at the University of Waterloo, was more specific. He said that the simplest explanation for what they are seeing is shifting, that it is looking more and more like they may need to modify the standard model of cosmology, and that evolving dark energy seems promising as the explanation. The signal in the data is not yet at the 5 sigma threshold that physicists consider the gold standard for a confirmed discovery. A 5 sigma result has a probability of occurring by chance of roughly 1 in 3.5 million. The Deci signal, depending on how the data is combined, ranges from 2.8 to 4.2 sigma. A 3 sigma result has a probability of being a fluke of about 0.3%. Many 3 sigma signals in physics have faded when more data arrived, but many have not. Adam Rees, one of the astronomers who discovered the acceleration of the universe and shared the 2011 Nobel Prize for it, said of the DESI results, "If it holds up, this is a very big deal. It may be the first real clue we have gotten about the nature of dark energy in the 25 years. Michael Turner, the cosmologist who coined the term dark energy, called it the best news he had heard since cosmic acceleration was firmly established more than 20 years ago. So what does evolving dark energy actually mean? What are the implications if the strength of the force driving the universe's expansion is changing over time? In the standard model, dark energy is constant. Every cubic meter of space contains exactly the same amount of dark energy, now and forever. As the universe expands, new cubic meters appear, and they are filled with the same energy density. Dark energy grows with the universe. Gravity, which acts on matter, becomes diluted as matter spreads out. Dark energy wins the battle. The expansion accelerates without limit. The big freeze is inevitable, but if dark energy is weakening, the calculation changes. A weakening dark energy loses ground against gravity over cosmic time. If it weakens enough, the expansion of the universe could slow, could stop, could reverse. Mustafa Ishaq Bouchaki, a professor of physics and astrophysics at the University of Texas at Dallas and a co-chair of a DESI working group, said in 2025 that if the dark energy results are correct, then eventually dark energy will not be the dominant force in the universe. The expansion will stop accelerating, and in some models it could stop and collapse back. Of course, these futures are very remote, he said, and will take billions and billions of years to happen, but the direction matters. If the universe is not locked into the big freeze, if the future is genuinely open, then we are living at a moment when the long-range forecast of everything is being revised. Carlos Frenk, a professor at Durham University and one of the architects of the Lambda CDM model, went further. He said that if the DESI hints are right, our earlier understanding of dark energy goes out the window. We would have to start from scratch. We would have to revise our understanding of basic physics, of the Big Bang itself, of the long-range forecast for the universe, starting from scratch. In cosmology, in 2025, the standard model has held for 30 years. It has survived every test. And now, the largest and most precise survey of the universe ever conducted is suggesting it may need to be changed, not discarded, not overturned, but modified in a way that has consequences for everything from the nature of empty space to the ultimate fate of the cosmos. The data are still coming in. DESI continues to observe. The Simons Observatory, currently under construction in Chile, will add new CMB measurements. The Euclid Space Telescope, launched in 2023, will add independent galaxy surveys. Over the next decade, the picture will sharpen. But for tonight, in the small hours, it is enough to know that the most fundamental force shaping the cosmos may not be what we thought it was, that the universe may be more complicated than our models, that the future may be more open than the equations suggested, and that somewhere in the machinery of dark energy, there may be a clue to what lies beyond everything we can see. Let the darkness hold that thought gently, because in the next chapter, we go somewhere even stranger. We follow the mathematics of inflation to a specific testable prediction, a prediction that says other universes may have already left their fingerprints on ours, and we ask whether we have already found them. Chapter 4, Continued, the Hubble Tension, a universe that disagrees with itself. While we are on the subject of what DESI and recent measurements have revealed about the universe, there is a second crack in the Standard Model that deserves attention. Because it is older than the DESI dark energy results, more stubborn, and in some ways more mysterious, it is called the Hubble tension. The Hubble constant is the number that describes how fast the universe is currently expanding. Specifically, it tells you how fast 2 points in the universe are receding from each other per unit distance. For every megaparsec of distance between 2 points, 1 megaparsec being roughly 3.26 million light-years, the expansion of absolute space adds approximately 67 to 73 kilometers per second to their recession speed. That range is the problem. There are two fundamentally different ways to measure the Hubble constant, and they give different answers. Not by a small amount, by enough to matter, by enough that if both measurements are correct, something in our standard model of the universe is wrong. The first method uses the early universe. The Planck satellite mapped the cosmic microwave background with extraordinary precision. And from those measurements, combined with the standard cosmological model, you can calculate the expansion rate of the universe today. That calculation gives approximately 67.4 kilometers per second per megaparsec. The second method uses the local universe. Astronomers use a chain of distance measurements, each one calibrated against the last, to build up a scale of cosmic distances. First, they measure the distances to nearby stars using parallax. Then they calibrate a class of variable stars called Cepheids, which pulse with a period related to their true brightness, allowing them to serve as standard candles at greater distances. Then they calibrate type 1a supernovae against the Cepheids, and use those supernovae to measure distances to galaxies billions of light years away. The expansion rate inferred from this chain of measurements is approximately 73 kilometers per second per megaparsec, 67 versus 73, a difference of about 10%, in measurements with uncertainties of a few percent. The two numbers are statistically incompatible at a level of roughly 5 sigma, which is precisely the threshold physicists consider sufficient to claim a discovery. In this case, the discovery is a discrepancy, a contradiction, two reliable methods giving two different answers for the same physical quantity. For many years, cosmologists hoped the tension was a systematic error in one of the measurements. Perhaps the Cepheid calibration was off. Perhaps the CMB analysis made an assumption that turned out to be wrong. Enormous effort has gone into checking both sides. The numbers persist. The most recent measurements have tightened the individual error bars rather than closing the gap. If the Hubble tension is real, it means one of two things. Either the early universe and the late universe are connected by a model that is missing something, some ingredient that changes the expansion rate between the early epoch, measured by the CMB, and the late epoch, measured by the local distance ladder. Or one of the measurements contains an unidentified systematic error. Many proposals have been made for new physics that could resolve the tension. Early dark energy, a form of dark energy that was active in the early universe but faded away, is one candidate. Interacting dark matter, which behaves differently from the cold dark matter in the standard model, is another. Modifications to general relativity at cosmological scales have been explored. None of these proposals has been confirmed. None fits all the data as well as the standard model fits most of it. And here is the connection to what we have already discussed. The DESI results of 2025 suggested that dark energy may be evolving over cosmic time. If dark energy is not a constant, but a quantity that changes, then the expansion history of the universe is different from what the standard model predicts, and a different expansion history affects how the early universe measurements connect to the late universe measurements. A changing dark energy might not resolve the Hubble tension, but it makes the problem richer and the solution more interesting. The Hubble tension and the evolving dark energy results are potentially two faces of the same underlying physics, two places where the Standard Model, the most tested cosmological model in history, is straining against the weight of new data. Will Percival, in discussing the DESI results, said that they are guided by Occam's razor, and the simplest explanation for what they see is shifting. That is a careful way of saying that the simplest model is no longer the best fit, that the universe is requiring more complexity to describe than the model assumes. This is how physics progresses, not through sudden revolutions usually, but through the slow accumulation of data that does not quite fit, through measurements that are a few sigma away from the prediction, through discrepancies that refuse to go away, and then, eventually, through a new framework that explains everything the old one explained in the discrepancies as well. We are, in 2025, in the discrepancy phase. The Hubble tension has been building for a decade. The dark energy evolution signal is strengthening. The Standard Model is showing cracks, and somewhere behind those cracks, there is a more complete description of the universe waiting to be found. It may involve a new understanding of dark energy. It may involve modifications to gravity at large scales. It may involve something no one has thought of yet. That last possibility is not a failure of imagination. It is the most honest statement of where we are. The universe has surprised us before. It discovered the expansion. Then it discovered the acceleration. Now it is suggesting that the acceleration itself may be changing. The next surprise is already in the data. We have not yet identified it clearly enough to name it. But it is there. The universe is telling us something. And the instruments we have built, from the Planck satellite to DESI to the Hubble Space Telescope to the James Webb Space Telescope, are listening. The data is accumulating, the picture is becoming more detailed, not simpler. And detail in science is always where the truth lives. For now, the honest answer to the question of what the universe is doing is something more complicated than we thought. And the honest answer to the question of what that means for what lies beyond our horizon is we are revising our understanding of the universe we can see, and that revision will eventually shape what we expect to find in the universe we cannot. The map is being redrawn, and we are the ones drawing it. Chapter 5. Bubble universes. When space collides. There is a specific prediction that emerges from eternal inflation, one that is different from all the others because it is, at least in principle, testable. Not with the instruments we have today, not with certainty, but testable in a way that the existence of distant pocket universes alone is not. The prediction is this: in an eternally inflating universe, pocket universes are constantly nucleating in the inflationary sea. They form when the inflaton field drops below a critical value in some region, ending inflation locally and releasing energy as a hot, dense plasma that then expands and cools into something that looks, from inside, like our Big Bang. These pocket universes are not spherical in the way a planet or a star is spherical. They form wherever the quantum fluctuations are right, and they grow from that point outward at close to the speed of light. If two such pocket universes form close enough together in the inflationary sea, close enough that they expand into contact before the inflating space between them can push them apart, they collide. Not the way two billiard balls collide, not the way two galaxies collide, something more subtle. Their boundaries meet, and the energy of that meeting leaves an imprint. That imprint would be visible in the cosmic microwave background. If our universe collided with a neighbouring pocket universe early in its history, the collision would have produced a disk of slightly different temperature in the CMB, a circular region. Perfectly circular, because the intersection of two spherical regions in three-dimensional space is always a circle, and the temperature profile across that disk would follow a specific mathematical pattern, one that can be calculated precisely from the theory. Physicists have looked for this. Stephen Feeney and Matthew Johnson and collaborators published a series of papers beginning in 2010, searching the WMAP data for circular temperature, anomalies consistent with bubble collisions. They found some candidates. They were careful to note that the candidates could be explained by chance. The statistical significance was not high enough to claim a detection, but they were not nothing. The search continues. The Planck satellite produced a more detailed map of the CMB than WMAP, and researchers have analysed that map as well, looking for the specific signatures that bubble collision models predict. As of today, no confirmed collision imprint has been found, but there is a feature of the CMB that keeps appearing in discussions of bubble collisions, and it is worth describing in some detail. It is called the cold spot. The cold spot was first noticed in the WMAP data in 2004 and subsequently confirmed in Planck data. It is a large region of the CMB that is significantly colder than expected, not slightly colder, approximately 70 microkelvin colder than the average, which sounds like a tiny number but is, in the context of CMB fluctuations, unusually large. The spot covers an area of roughly 10 degrees on the sky, which corresponds to an enormous physical scale, much larger than the typical CMB fluctuations. Various explanations have been proposed. One of the most discussed is a supervoid, a region of space with fewer galaxies than average, whose gravitational effects on photons passing through it could produce a cooler signature in the CMB. And indeed, astronomers have found evidence of a supervoid in the direction of the cold spot. But whether the supervoid is large enough and deep enough to fully explain the temperature anomaly is still debated. Could the cold spot be the remnant of a collision with a neighbouring bubble universe? Most cosmologists who have studied it carefully say probably not. The statistical case for a bubble collision interpretation is not strong. The supervoid explanation, while incomplete, is more straightforward. But the cold spot remains anomalous, unexplained with full confidence, and it continues to attract attention. The deeper point here is not that the cold spot is definitely a bubble collision signature. The deeper point is that bubble collisions are a genuine, calculable prediction of eternal inflation. They produce specific observable signatures. We know what to look for. And the fact that we have not yet found a confirmed signal does not mean the signal is not there. It may mean our instruments are not yet sensitive enough, or our sky coverage is not yet complete enough, or the collisions, if they happened, produce signatures below the current noise floor. The next generation of CMB experiments will push the sensitivity significantly further. The Simons Observatory, being built in the Atacama Desert of Chile, will map the CMB polarization with far greater precision than Planck. The CMB-S4 experiment, a collaboration involving multiple countries and dozens of institutions, will push further still. If bubble collision signatures exist at the levels that inflationary models predict, these instruments have a realistic chance of finding them. And if they do find a circular anomaly, with the right temperature profile in the right location, with the right polarization pattern, it will be the most consequential observation in the history of science. It will be direct evidence that our universe is not alone. We are not there yet, but we are looking. And the fact that we know what to look for, that inflation makes specific predictions, not vague suggestions, but mathematical calculations with predicted amplitudes and angular profiles, is itself remarkable. It means the multiverse, which sounds like pure speculation, is at least partially constrained by observation. Let that idea carry you forward. The universe we inhabit may already bear the scars of contact with another. The cold region of sky you could point to on a star chart, roughly in the direction of the constellation Eridanus, may be where something beyond our universe touched ours. Or it may be a supervoid. Science lives in that uncertainty, and does so without discomfort, because the next measurement is always coming. The next observation is always being designed. The search does not stop. The map is always being refined. And in that spirit, let us go deeper. Let us follow the logic of inflation into the landscape of string theory. where the number of possible universes is not just large but almost incomprehensible. Chapter 6. The String Theory Landscape, 10 to the power of 500. String theory is an attempt to do something that has eluded physics for a century, to write down a single coherent mathematical framework that describes all of nature, from the quantum behaviour of the smallest particles to the large-scale structure of the cosmos, without internal contradictions. Standard quantum mechanics, which describes the behaviour of particles with extraordinary precision, is fundamentally incompatible with general relativity, Einstein's theory of gravity. They work beautifully in their respective domains. Quantum mechanics governs atoms and subatomic particles. General relativity governs planets, stars, and the large-scale structure of space. But when you try to apply quantum mechanics to gravity directly, the equations produce nonsense. Infinite answers, divergences that cannot be removed. The two theories cannot be the same theory, and yet they both describe the same universe. String theory proposes that the fundamental entities in nature are not point particles, but one-dimensional vibrating strings of energy, unimaginably small, roughly at the Planck scale of 10 to the negative 35 meters. Different vibrational modes of a string correspond to different particles. A string vibrating in one mode is an electron. Vibrating in another, it is a photon. Vibrating in another, it is a graviton, the hypothetical carrier of gravity. String theory naturally includes gravity. It naturally avoids the infinite divergences that plague other attempts at quantum gravity. But string theory comes with complications. To be mathematically consistent, it requires not 4 dimensions of space-time, the 3 spatial dimensions and 1 time dimension we experience, but 10 or 11. The extra dimensions must be curled up into a tiny compact space, too small to detect with any instrument. And there are many, many ways to curl up those extra dimensions. Different geometries for the compact space produce different physics in the 4 dimensions we can observe. Different values for the fundamental constants, different particle masses, different forces. The number of possible ways to compactify the extra dimensions of string theory is estimated at approximately 10 to the power of 500. Each compactification corresponds to what physicists call a vacuum state, and each vacuum state corresponds to a universe with its own physical laws. 10 to the power of 500 universes. The physicist Leonard Susskind at Stanford University, one of the founders of string theory and one of the most important physicists of the last half century, has called this the landscape of string theory, a vast terrain of possible universes, each with its own physics, each potentially real if inflation provides the mechanism to populate them. Susskind was initially reluctant to embrace this conclusion. When the cosmological constant was discovered to be non-zero in 1998, he and others began working out what string theory predicted about its value. What they found was that the landscape of string vacua produces a distribution of possible cosmological constant values that includes values as small as the one we observe. Not as a fine-tuned coincidence, as a natural consequence of the sheer number of possibilities. In an infinite multiverse of pocket universes, each settling into a different string vacuum, our universe is one of the small fraction, where the cosmological constant is small enough to allow galaxies to form. We are here because we are in one of those universes. This is the anthropic principle applied at a scale that makes previous applications look modest. Steven Weinberg, whose 1987 prediction about the cosmological constant was borne out by the 1998 observations, had argued that the cosmological constant must be small, because if it were much larger, galaxy formation would have been suppressed, and no observers would exist to measure it. His prediction assumed a multiverse implicitly. The stringed landscape provides the mechanism. Together, they form a coherent, if deeply unsettling picture. The discomfort that many physicists feel about the landscape is real and worth taking seriously. if every possible configuration of physics is realized somewhere in the multiverse, then physics loses its predictive power in a certain sense. You cannot derive the electron mass from first principles if the electron mass is simply whatever it happens to be in our particular vacuum. You can only observe it and note that it is compatible with our existence. David Gross, another Nobel laureate in physics, has been among the sharpest critics of the landscape. He has argued that accepting it as an explanation is equivalent to giving up on physics, that it replaces the dream of a final theory, a single equation from which all of nature follows, with an infinite library of possibilities and an anthropic shrug. Susskind disagrees. He argues that the landscape, uncomfortable as it is, may simply be what is true, that nature is not obligated to produce a unique, elegant, derivable set of physical laws, that the job of science is to figure out what is true, not what is beautiful. This debate is not resolved. It is one of the most active and consequential debates in theoretical physics today, and it will not be settled by philosophy. It will be settled, if it is settled at all, by observation. If experiments at the Large Hadron Collider or its successors find evidence for supersymmetric particles or other signatures of string theory, the landscape will gain credibility. If they find nothing, theorists will have to reckon with that. Chapter 6. Continued. The Planck scale and the limit of knowledge. There is one more layer to add here, one that is so fundamental it underlies all of the theories we have discussed. All of these ideas, inflation, eternal inflation, the string landscape, bubble universes, all of them break down at a specific scale, the scale where quantum mechanics and gravity become equally important, the scale where our two great theories of the universe, which work perfectly in their respective domains, collide with each other in a way that current physics cannot resolve. This scale is called the Planck scale. The Planck length is approximately 1.6 times 10 to the negative 35 meters. That is 10 to the 20th times smaller than a proton. It is the smallest length scale that has any physical meaning in current physics. Below the Planck length, our equations tell us nothing reliable, because quantum fluctuations of space-time itself become so large that the very concept of a smooth, continuous space breaks down. The Planck time is approximately 5 times 10 to the negative 44 seconds. It is the smallest interval of time that has any physical meaning. Before the Planck time after the Big Bang, before the first 5 times 10 to the negative 44 seconds of the universe's existence, we have no theory that can tell us what was happening. The equations simply stop working. This is not a failure of the physicists who wrote the equations. It is a fundamental limitation of the theories. General relativity, which describes gravity and the large-scale structure of space-time, is a classical theory. It treats space-time as smooth and continuous. Quantum mechanics, which describes the behavior of particles and fields at small scales, is a quantum theory. It treats quantities as discrete and probabilistic. At the Planck scale, both effects are equally important simultaneously. You need a theory of quantum gravity, and we do not have one. String theory is the leading candidate for such a theory, which is one reason the string landscape is taken seriously by so many physicists. Loop quantum gravity is another approach. Causal dynamical triangulations is another. These are active areas of research, with thousands of physicists working on them, and the question of which, if any, correctly describes quantum gravity remains open. But here is the connection to what lies beyond our observable universe. The initial conditions of inflation, the state of the universe before inflation began, the state from which our entire cosmos descended, were set at or near the Planck scale. The inflationary universe was, before inflation stretched it, smaller than the Planck length. The quantum fluctuations that seeded every galaxy, every star, every planet, every person, were quantum fluctuations at the Planck scale, stretched by inflation to cosmic dimensions. Understanding what happened at and before the Planck time is, therefore, not just a matter of abstract physics. It is a matter of understanding where we came from, understanding the initial conditions of the universe, understanding whether our universe had a beginning in any meaningful sense, or whether it emerged from something else, something in the inflationary sea or in the string landscape or in a cyclic sequence of universes that stretches back further than any current theory can address. The physicist Roger Penrose at Oxford University has spent decades working on a model called conformal cyclic cosmology, in which the universe undergoes an infinite sequence of aeons, each one beginning with a Big Bang and ending with a heat death, and the heat death of each aeon seeding the Big Bang of the next through a conformal matching of the geometry of space-time. In this model, what lies beyond our universe in time is not nothing. It is the previous aeon, and within the CMB, Penrose and his collaborators claim to have found hints of circular patterns that could be relics of the previous aeon, of massive black hole collisions that occurred before our Big Bang. These claims are controversial. Many CMB researchers have examined the Penrose circles and concluded that they can be explained by chance within the standard model. The debate continues. But the very existence of the proposal and the seriousness with which it is taken illustrates something important. The question of what lies beyond our observable universe is not a question that physicists have given up on. It is a question they are actively attacking from multiple directions, using every tool available, from satellite measurements to theoretical mathematics, to debates about the nature of time. The universe beyond our horizon is not inaccessible to thought. It is only inaccessible to direct observation, and thought, careful thought, disciplined by mathematics and constrained by observation, has taken us further than any physical journey could. It has taken us to the edge of the observable universe and kept going. It has told us about the inflationary sea and the string landscape and the Planck scale and the long future of the cosmos. It has told us tentatively, but honestly, that what lies beyond what we can see is almost certainly more, probably much more, and possibly infinite. And that knowledge, incomplete as it is one of the most extraordinary things the human mind has ever produced. For now, the string landscape stands as the most fully developed theoretical framework for what lies beyond our observable universe. It says that the region of space we inhabit is one small corner of a vast terrain of possible physics, that the constants we measure are not unique or necessary, that an infinite variety of other physical realities exist, each one as real as ours, each one governed by different rules, most of them empty and silent, a small fraction of them complex and perhaps inhabited. Whether any of those inhabited universes contain beings asking the same questions we are asking tonight is a question that physics cannot yet answer. The distances involved make it unanswerable by observation. But the mathematics leaves it open, and leaving a question open is not the same as having no answer. It is the beginning of the search. Chapter 7. The geometry of everything. What shape is space? There is a question that sits underneath everything we have discussed so far. It is a question that looks technical, but turns out to be one of the deepest in all of science. And it is this: what is the shape of space? Not the shape of the observable universe, that is roughly spherical, bounded by our cosmic horizon. The shape of space itself, the total geometry of the cosmos, including everything we cannot see. There are three possibilities, and each one implies a different answer to the question of what lies beyond our horizon and how much of it there is. The first possibility is that space is flat. This is the configuration suggested by our measurements of the CMB, the configuration predicted by inflation, the configuration implied by a universe right at the critical density of matter and energy. In flat space, the geometry is Euclidean. Parallel lines never meet. The angles of triangles add up to 180 degrees, and flat space, if it extends in all directions without boundary, is infinite. We have been assuming this for most of tonight. The flat universe, the infinite universe, the universe that extends forever in every direction, filling with the same physics, the same galaxies, the same arrangements of matter. repeating indefinitely. If space is flat, this is what we have. Infinity, in every sense of the word. The second possibility is that space is positively curved, like the surface of a sphere, but in 3 dimensions. In a positively curved universe, parallel lines eventually meet. Triangles have angles that add up to more than 180 degrees, and crucially, a positively curved universe is finite. It has no edge, no boundary, no wall, but it has a definite size. If you travel far enough in any direction, you return to your starting point. Just as travelling in a single direction on the surface of a sphere eventually brings you back to where you started. How large would a positively curved universe have to be? The curvature of space would have to be extremely small, far below the current measurement uncertainty of the CMB flatness measurements to have escaped detection. Physicists have calculated the constraints. Based on the current data, a finite positively curved universe would have to be at least a few 100 billion light-years across. Some estimates, depending on how conservatively you interpret the measurement uncertainties, put the lower bound at roughly 23 trillion light-years in diameter. 23 trillion light-years. The observable universe is 93 billion light-years across. A positively curved universe would have to be at least 250 times larger than what we can see, possibly much more. In a positively curved universe, the infinity of matter and the infinite repetition of configurations disappears. There is only a finite amount of space, a finite amount of matter, a finite number of possible histories. The universe is large, but it is bounded, and you in it are unique. There is no copy of you somewhere beyond the horizon, because there is no infinite beyond the horizon. There is only a vast curved finite cosmos looping back on itself. The third possibility is that space is negatively curved, like the surface of a saddle. In negatively curved space, parallel lines diverge. Triangles have angles that add up to less than 180 degrees, and negatively curved space, like flat space, extends infinitely, but it expands faster, in a geometric sense. The volume of a negatively curved space grows more rapidly with distance than flat space does. Our current measurements are most consistent with flat space, but the measurements have error bars, and within those error bars a small positive or negative curvature is possible. This is the honest scientific position. We cannot measure the total shape of the universe. We can only measure it to within a certain precision, and within that precision, it looks flat. There is a further complication that deserves attention, because it is one of the more beautiful ideas in the study of the universe's shape. Even a flat universe need not be infinite. This sounds paradoxical, but geometry allows for it. Consider a two-dimensional square. If you connect the left edge to the right edge, you get a cylinder. If you then connect the top edge to the bottom edge, you get a torus, a donut shape. The surface of a donut is flat, in the mathematical sense that a flatlander living on its surface and drawing triangles would find that the angles add up to 180 degrees, but the surface is finite. You can travel in one direction and eventually return to your starting point. The same logic applies in 3 dimensions. A 3-dimensional space could be flat, in the sense that Euclidean geometry holds locally, but have a topology that causes it to wrap around on itself. If you travelled far enough in one direction, you would return from the opposite direction. The universe would be finite, but have no edge. This topology is called a flat torus, or more generally a multiply connected topology. Physicists have searched for evidence of it in the CMB. If the universe has such a topology, and its repeat length is smaller than our observable sphere, then we should see repeating patterns in the CMB. We should see identical spots in different parts of the sky, because we are seeing the same regions of space from different angles. The Planck satellites searched for these patterns extensively. No confirmed evidence of a compact topology was found. If the universe does have a compact topology, its repeat length must be at least as large as our observable universe, probably larger, which means, even if the universe is finite and topologically wrapped, we cannot detect its wrapping from within our horizon. It simply looks flat and boundless from where we sit. This brings us to the deepest and most honest statements we can make about the shape of the universe. We do not know. We know it is very close to flat. We know it is very large. We know it could be infinite or could be very large and finite. We know it might have a complex topology that we cannot detect from within our horizon. What we do not know is the thing we most want to know, whether there is a somewhere else, whether space ends or wraps or simply continues without limit. And here is the strange peace that this uncertainty offers, if you are willing to accept it. The universe does not owe us an answer we can verify. It is not required to be the size or shape that our instruments can resolve. It is required only to be what it is, and what it is, as best as we can determine from the evidence, is vast beyond any intuitive meaning of the word vast, old beyond any intuitive meaning of the word old, complex beyond any theory we have yet assembled, and still, in many essential ways, unknown. We are in the position of a person who has just discovered that the room they are standing in is actually a vast hall, and who, looking toward the far end of the hall, can just barely make out another room beyond it, and who cannot be certain whether that next room leads to another, or whether it simply continues forever, or whether, in ways they do not yet have the mathematics to describe, it curves back upon itself. The measurement is ongoing. The next generation of experiments is being built. The question remains open. Chapter 7. Continued. The deepest question. There is a sense in which the question of the universe's geometry is the deepest question in cosmology, not because the geometry determines the fate of the cosmos, though it does, not because it determines whether space is finite or infinite, though it does that too, but because the geometry of the universe is, in a fundamental sense, the geometry of existence. Of all the existence there is, of the container in which every event that has ever occurred, every particle that has ever interacted, every thought that has ever been thought, every measurement that has ever been made, all of it happens. If space is infinite, then existence is infinite. There is no limit to how much of it there is. Infinity plus infinity equals infinity. There is room for everything that can happen, to happen infinitely many times, and still room for more. If space is finite, then existence is finite. There is a definite amount of it, a very large amount, but a bounded one, and within that bounded amount the sum total of all events, all particles, all histories, is a number you could, in principle, write down. Very large, but finite. These two possibilities are not emotionally equivalent. The infinite universe is in some ways harder to live with. It is harder to feel significant in an infinite universe. Any finite thing, compared to infinity, is essentially nothing. Your life, the history of your civilization, the history of your planet compared to infinity, is not even a rounding error. The number is zero in any meaningful comparison to the infinite. But the finite universe has its own difficulties. If existence is finite, then it has an edge. Not a physical edge necessarily, not a wall you could fly your spacecraft into, but a logical edge, a boundary beyond which there is no more. And what lies beyond that boundary is a question that cannot be answered within the terms of the universe itself. Philosophers have been wrestling with this for millennia. Long before physics had anything useful to say about the shape of the universe, thinkers were asking whether space can be finite and whether something lies beyond its limits. Aristotle argued that the universe must be finite because he could not conceive of actual infinity. The Stoics argued it was infinite. The medieval theologians argued that beyond the universe lay God, the only thing that could exist outside of space and time, and the question has never been settled, because the question reaches beyond what any scientific instrument can resolve. Physics gives us the best tools we have for approaching this question. The CMB tells us about the geometry. The distribution of galaxies tells us about the topology. The behavior of dark energy tells us about the future. But the question of whether the universe is finite or infinite is, at the level of precision our current instruments can achieve, still open. And perhaps there is something important in that openness. Perhaps the universe is not the kind of thing that resolves all its own questions. Perhaps some questions reach beyond the accessible, not because they are meaningless, but because they point to the parts of reality that we cannot see. The parts beyond our horizon, the parts in the inflationary sea, the parts in the string landscape, the parts, if cyclic cosmology is right, in the sequence of universes before and after ours. The universe beyond our horizon is real. It is governed by the same laws. It contains the same kinds of structures. It may or may not contain observers asking these same questions, and we will never reach it. We will never observe it directly. We will only ever know it through the implications of the physics we can observe here. That is not a failure of science. It is the condition of science. In a universe with a finite age and a finite speed of light, we are limited not by the inadequacy of our instruments, but by the structure of space-time itself. The cosmic horizon is a fundamental feature of a universe with a Big Bang. It is baked into the geometry of the situation. But within the horizon, we are learning. The picture is getting more detailed. The uncertainties are shrinking in some areas, while growing more precise in others. The Hubble tension is real and persists. The dark energy evolution signal is strengthening. The James Webb Space Telescope is showing us galaxies from before any theory expected them. The Planck satellite has given us the most precise map of the CMB ever made. And from all of this we are building a description of what lies beyond our horizon that is, in a genuine sense, the best one humanity has ever had. Not perfect, not complete, but better than the one we had before, and better again than we will have tomorrow, when the next observation comes in and the picture shifts. The universe rewards patience. It rewards careful measurement. It rewards the willingness to be wrong and to revise. And it rewards, perhaps more than anything, the willingness to keep asking, even when the answers are incomplete, even when they raise more questions than they settle, even when the edge of knowledge is so far out in the dark that you can barely make it out. The edge of everything we can see is 46.5 billion light years away, but the question of what lies beyond it has no edge at all. It keeps going, just like the universe itself, which does not stop expanding because we stop looking, which does not pause the production of new stars because no one is watching, which does not halt the generation of new pocket universes in the inflationary sea because we have reached the limit of what our telescopes can detect. The universe is indifferent to our observation of it. It was here before we were. It will be here after we are gone. And whatever lies beyond our horizon, whatever fills the infinite space between here and the repetition of this exact configuration of atoms somewhere in the vast dark, it is all happening right now, quietly, continuously, without our attention and without our knowledge and without our permission. And somehow, that is the most restful thing of all. The universe does not need us to keep track of it. It keeps track of itself, with mathematics, with physics, with the simple relentless operation of the laws of nature which do not pause, do not hesitate, do not err. You can let go of it for tonight. And open questions, held lightly in the dark, are among the best things to fall asleep to. Chapter 8. Extended. The Long Future. Before we arrive at what all of this means for tonight, for rest and for the particular form of wonder that sleep carries with it, there is one more piece of the story worth telling, because we have talked extensively about what lies beyond the observable universe in space, but there is another dimension to the question. What lies beyond the observable universe in time? The universe has a future, a very long one, and what lies at the end of that future, or what comes after it if there is an after, is one of the most extraordinary subjects in all of physics. In the standard model, with dark energy as a constant, the future of the universe is the Big Freeze. Galaxies currently visible to us will, over the next tens of billions of years, gradually recede beyond our cosmic horizon. The accelerating expansion will carry them away faster than light can cross the growing distance. They will not disappear all at once. They will dim. they will redshift. Their light will stretch to longer and longer wavelengths, and eventually they will fade completely beyond any instrument's detection, not because they're gone, but because the space between us has expanded so much that no signal from them can ever reach us again. The last galaxies to fade will be the ones in our local supercluster, the Virgo supercluster, and the other clusters and groups gravitationally bound to our own neighbourhood. Gravity can hold things together even against the expansion of space, as long as the structures are dense enough and close enough. The Milky Way and Andromeda will merge in approximately 4.5 billion years, forming a larger elliptical galaxy. The local group of galaxies will remain bound together for much longer, but eventually even the local group will be all that remains visible to any observer in the Milky Way's successor galaxy. After that, the timeline stretches into a kind of grandeur that can only be expressed in scientific notation. The stars will continue to burn for tens of trillions of years. The smallest, most efficient stars, red dwarfs with masses around 1/10 of the Sun's, will burn hydrogen so slowly that they will last for 10 to the 13th years, 10 trillion years. The Sun's total lifespan is approximately 10 billion years. The longest-lived red dwarfs will outlast it by a factor of 1,000. After the last stars exhaust their fuel, the universe will be dark, not completely empty. Stellar remnants will persist. White dwarfs, the crystallized cores of dead sun-like stars, will gradually cool over trillions of years. Neutron stars, the ultra-dense remnants of massive stellar explosions, will cool more slowly still. Black holes will dominate the mass budget of the cosmos, growing over cosmic time as they swallow what little matter comes their way. And then slowly, on timescales that make the current age of the universe look instantaneous, even the black holes will evaporate. Stephen Hawking showed in 1974 that black holes are not perfectly black. Quantum mechanical effects near the event horizon cause them to radiate energy very slowly, losing mass and eventually, over an extraordinarily long time, evaporating completely. A black hole with the mass of the Sun would take approximately 10 to the 67th years to evaporate. A supermassive black hole at the centre of a large galaxy, with a mass billions of times the Sun's, would take approximately 10 to the 100th years. That number, 10 to the 100th, is called a googol. The universe is currently about 1.38 times 10 to the 10th years old. Supermassive black holes will outlive the current age of the universe by a factor of 10 to the 90th. After the last black hole evaporates, what remains is a sparse, cold, vast sea of particles, mostly photons and neutrinos and perhaps some electrons and positrons, with nothing left to form structures. No gravity strong enough to pull matter together. No energy source to drive any process. The universe reaches what physicists call maximum entropy. Heat death, the big freeze, a final state of perfect featureless equilibrium from which nothing can emerge because there are no gradients of energy left to drive any change. This is the standard forecast. Dark energy as a constant. Big freeze as the end. But the DESI results of 2025 have opened the question. If dark energy is weakening, the future is different. A weakening dark energy loses ground to gravity over cosmic time. The expansion, currently accelerating, could eventually slow, could halt, could reverse. And if it reverses, the future of the universe is not the big freeze but the big crunch. Everything that has spread apart over billions of years comes back together. The cosmic web of galaxies contracts. Galaxy clusters merge. Individual galaxies fall toward each other, stars collide, gas is compressed and heated, and at the end the entire mass of the universe is compressed back into a state as dense and hot and small as the beginning. What lies on the other side of a big crunch, if there is another side, is something physics in its current form cannot describe. The equations of general relativity break down at infinite density, just as they break down at the initial singularity of the Big Bang. We do not have a theory of quantum gravity complete enough to say what happens in those conditions. We do not know whether the universe bounces, whether a new Big Bang emerges from the crunch, whether the collapse generates the conditions for a new cycle of expansion. Some models in string theory and loop quantum gravity suggest it might. These are called cyclic cosmologies, and they propose that the universe undergoes an eternal sequence of big bangs and big crunches, each cycle separated by a period of expansion. If cyclic cosmologies are right, then the question of what lies beyond our observable universe in time has an answer as strange as the answer in space. Beyond the future end of this universe, there may be another universe, not a bubble universe in the inflationary sea, not a parallel pocket in the multiverse, but a sequential universe, the next iteration of the same cosmos, beginning again from a different set of initial conditions, going through its own Big Bang and expansion and structure formation, and perhaps its own observers asking these same questions. The Russian physicist Alexander Friedmann, who first derived the equations describing an expanding universe in the 1920s, was drawn to this idea. He thought the universe might be cyclic. Einstein thought it was interesting. The mathematics allowed it. Whether nature realizes it is a question that depends on the true nature of dark energy and the behavior of matter at extreme densities, both of which are active areas of research today. For tonight, it is enough to know that the future of the universe is genuinely open. The standard forecast is the big freeze, but it is conditioned on dark energy being constant, and that condition is being tested right now by DESI and the instruments that follow it. The alternative futures, big crunch or cyclic or something else entirely, are not science fiction. They are mathematically consistent with the equations of general relativity and with some extensions of the standard model. The data will tell us which over the coming decades, and there is something oddly comforting about a future that is open, about a universe whose long-range forecast is being revised. The universe has more room in it, in time as well as in space, than the standard model assumed, and more room means more possibility, more story, more of whatever comes next. The universe is not finished, not in space, where it extends far beyond what we can see, and perhaps forever. Not in time, where it has billions upon billions of years of future ahead of it, and perhaps more beyond that. And not in what it is capable of producing, because it has only been at the project of making complex structures for 13.8 billion years, and the longest-lived stars have trillions of years still ahead of them. The universe is young, embarrassingly young, by the standards of its own future. We are living near the beginning, and near the beginning of a very long story is a wonderful place to be, particularly when you are warm and still and resting, and the story will still be going on long after tonight is over. Chapter 8. What it all means. The edge of everything. We have travelled a long way together tonight. Let us trace the path back. We began with the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. It is 93 billion light years across. At its edge is the cosmic microwave background, the oldest light in the universe, released 380,000 years after the Big Bang when the cosmos first became transparent. The light carries information about the shape of space, and the information it carries says that space, as best we can measure, is flat. If space is flat, it is probably infinite, and if it is infinite, then beyond our horizon the same universe continues, with the same physics, the same structures, the same laws, and in an infinite universe every possible configuration of matter recurs infinitely, which means that somewhere, impossibly far away, this moment is being repeated. Then we went deeper. We followed cosmic inflation, the theory that the universe underwent a period of exponential expansion in its first moments, stretching a microscopic patch into the cosmos we observe. Inflation, carried to its logical conclusion by Alan Guth and Andrei Linde and Alexander Vilenkin and many others, produces eternal inflation, a universe where the inflationary process never stops completely, but constantly generates new pocket universes in the vast sea of expanding space. Our universe is one of those pockets, and around us right now, new pockets are forming. Then we sat with the DESI results of 2025. the largest three-dimensional map of the universe ever constructed, a map that spans 11 billion years of cosmic history and contains the spectra of nearly 15 million galaxies. A map that, when combined with the CMB data, supernova measurements and gravitational lensing surveys, suggests that dark energy, the force driving the universe's accelerating expansion, may not be constant. It may be weakening. And if it is weakening, the future of the universe is not the big freeze we assumed. It may be something else entirely. Something more open. Something we do not yet have the mathematics to fully describe. Then we followed the bubble universe prediction. The idea that in an eternally inflating cosmos, neighbouring pocket universes occasionally collide, and those collisions leave specific calculable imprints on the cosmic microwave background. We looked at the cold spot. We asked whether it might be a scar from contact with another universe. We concluded honestly that probably not, but that the search is ongoing, and that the next generation of CMB experiments may give us an answer. Then we entered the string landscape, 10 to the power of 500 possible universes, each with its own physics, each real in the sense that eternal inflation can populate them. A landscape so vast that no intuition can hold it. A landscape that may explain why the constants of nature have the values they have, but at the cost of making those values in some sense arbitrary, selected by the accident of which vacuum state our particular pocket of the multiverse settled into. And then we asked about the shape of space, flat or curved, infinite or finite, topologically simple or topologically wrapped, and we arrived at the honest answer, which is that we do not know. The measurements constrain but do not determine. The universe is very close to flat. It is very large, and whether it ends or continues or loops back on itself remains, in 2025, an open question. These are not comfortable conclusions. They are not the kind of answers that close down questions and leave you feeling settled. They are the kind of answers that open up more questions, deeper questions, questions that may not be answerable in any human lifetime. And that is appropriate, because the universe is not designed for human comfort. It is not scaled to human intuition. It is simply what it is, and what it is turns out to be far stranger and far larger and far more mysterious than anything our ancestors imagined when they first looked up at the night sky. But there is a different kind of comfort available, not the comfort of resolution, the comfort of perspective. You are lying right now in a specific arrangement of atoms on a planet that is one of at least 8 in a solar system, that is one of perhaps 400 billion in a galaxy, that is one of at least 2 trillion in the observable universe. The observable universe that is 93 billion light years across and expanding. The observable universe that is, according to the best theory we have, for why it looks the way it does, an infinitesimal fraction of a larger cosmos in which new universes are constantly being born. You are impossibly small, and you are, as far as we know, one of the only arrangements of matter in this tiny corner of the cosmos that has developed the capacity to wonder about these things, to build telescopes, to launch satellites, to measure the angles of cosmic triangles and deduce the shape of space, to look at the distribution of 15 million galaxies and ask whether the force driving their separation might be changing. The universe has, in you and in every person who has ever looked up at the night sky and had asked why, produced something that turns back on itself and tries to understand. That is not a small thing. In a cosmos of perhaps infinite silence and darkness and empty physics, that is an extraordinary thing. And it is worth lying still and holding that for a moment. The universe beyond our horizon continues without us. It does not need our observation to exist. It was there before we evolved to look for it, and it will be there long after the last star in the observable universe has burned out. The inflationary sea, if it exists, has been generating new universes since before our Big Bang. The string landscape, if it is real, contains more possibilities than the mind can hold, but all of that is not somehow diminishing. It does not make this moment smaller, it makes it more precise. carves this moment out of an incomprehensible vastness and says, here is where it is happening. Here is where the universe is right now, aware of itself. 13.8 billion years of expansion, of stars forming and dying, of galaxies colliding and separating, of dark energy pushing space apart at an accelerating rate, of quantum fields fluctuating in ways that seeded every structure you can see, and the whole long, improbable story led, among other places, to this. A voice in the dark. A mind listening. Questions that reach all the way to the edge of the observable universe and keep going. The cosmic microwave background is still travelling. Right now, photons that set off 13.8 billion years ago are passing through the walls of wherever you are, through the air around you, through your body. They have been travelling since 380,000 years after the beginning of time, crossing the entire observable universe, carrying information about what things were like when matter first became transparent. They are ancient beyond any intuitive meaning of the word ancient, and they pass through you, unimpeded, unremarkable, every second of every night. The universe is not separate from you. You are inside it, made of atoms forged in stars that exploded billions of years ago, scattered through the galaxy, assembled by gravity and chemistry into the particular shape you occupy tonight. The iron in your blood was made in the core of a massive star that ended its life in a supernova. The carbon in your bones was assembled in the helium-fusing shell of a dying giant. The oxygen you breathe was released by the first photosynthesizing organisms on a planet that has been alive for 4.5 billion of the universe's 13.8 billion years. You are old, not you personally, but the matter that comprises you is genuinely, cosmically old. And it came from a place, from the interiors of dead stars and the primordial plasma of the early universe, that connects you to everything we have been describing tonight. The edge of the observable universe is 46.5 billion light years away. Beyond it, space continues. The physics continues. The same laws apply to the same ingredients, producing variations on familiar themes. And beyond that, if inflation is right, the inflationary sea generates more. And in that sea, what lies beyond is not nothing, not silence, not an end, just more universe, in every direction, without limit, still expanding, still cooling, still in its quiet mathematical way, extraordinary. Let that be what you carry into sleep tonight. Not the anxiety of infinite space, not the vertigo of geological time, but the simpler version of the same thought. You are here, in a universe that is 93 billion light years across and probably larger, in a cosmos that has been running for 13.8 billion years, on a planet that formed from the debris of dead stars, in a body made of atoms as old as the solar system, lying still, in the dark, while photons from the edge of time pass through the room. The universe is still going. It does not need your attention to continue. You can rest now. You can rest. The cosmos will still be here when you wake up. The expansion will continue. The dark energy, whatever it is doing, will keep doing it. The inflationary sea, if it exists, will keep producing new universes in the silent distances beyond our horizon. The cosmic microwave background will keep travelling. Those ancient photons spreading across the void. None of it requires anything from you tonight. The equations will hold. The measurements will continue. The telescopes will keep observing. DESI will add more galaxies to its map. The Simons Observatory will measure more polarization in the CMB. The Euclid Space Telescope will map the large-scale structure of the cosmos with new precision. All of it is continuing quietly in the background, the way a river continues to flow whether or not anyone is watching it. And you, in the middle of this vast and ancient and still expanding universe, can let go of the scale of it for tonight. The scale is real. The questions are real. The uncertainty is real. But they will all still be there tomorrow. The edge of the observable universe is not going anywhere. The puzzle of dark energy is not going anywhere. The string landscape is not going anywhere. They will wait. Sleep is not an abandonment of wonder, it is a return to the simplest fact of being alive, that this particular arrangement of atoms in this particular corner of an incomprehensibly large cosmos needs rest. And rest is not a small thing, it is what makes the questions possible, it is what makes the telescopes get built, it is what makes a physicist stay late in a laboratory in 1979 and write, in a diary, the words spectacular realization. Sleep is where tomorrow's wonders are prepared, so let the universe go on without you for a few hours. It has been doing it for 13.8 billion years. It knows how. Close your eyes, let the words become quieter. Let the scale of things recede until it is just a feeling at the edges of your awareness, a vastness that is somehow comfortable rather than frightening, because you know where you are in it. You are here. You are warm. You are resting. The cosmic microwave background is 2.725 degrees above absolute zero. That is almost as cold as space gets. But here, right where you are, it is warmer than that, considerably. And that warmth is, in the grandest sense of the word, the point. Stars burn to make the atoms in your body. Gravity assembled those atoms into you. The universe, in its long, slow, indifferent way, arranged itself so that arrangements like you are possible, so that questions like the ones we have been asking tonight are possible. That is not nothing. That is in fact almost everything. Rest well. The edge of the observable universe is 46.5 billion light years away. It is not going anywhere. It will still be there when you wake up, still expanding, still sending those ancient photons outward through the dark, and beyond it, as best as the physics can determine, something continues. Just more. Just more. Sleep now. Epilogue. A final thought before sleep. There is one more thing, one small thing worth holding in the last moments before sleep comes. Every civilization that has ever existed on Earth, every person who ever looked up at the night sky in wonder or in fear, every astronomer who ever traced the movement of stars across the sky, every physicist who ever wrote equations describing the behavior of light, every engineer who ever built a telescope, every satellite that ever mapped the CMB, every researcher who ever stayed late analysing galaxy spectra from DESI, every human being who ever asked where all of this came from and what lies beyond the horizon of what we can see, all of them were doing the same thing. They were the universe looking at itself. Not in a poetic way, in a literal way. The atoms that comprise a human brain, the neurons that fire in patterns that constitute thought, the questions that those thoughts produce, all of it is made of matter that came from the Big Bang, matter that was forged in stars, matter that is, in the most technical and literal sense, a part of the universe arranging itself into a configuration capable of self-reflection. When Alan Guth sat in his office at the Stanford Linear Accelerator Center in the autumn of 1979 and worked out the mathematics of inflation, the universe was understanding itself. When the Planck satellite mapped the CMB and showed that space is flat to within 1%, the universe was measuring itself. When the DESY collaboration released their results in March of 2025 and suggested that dark energy may be evolving, the universe was revising its understanding of itself. When the James Webb Space Telescope resolved a galaxy from 290 million years after the Big Bang and found it more massive and more structured than the models expected, the universe was, in a meaningful sense, surprising itself. Science is the universe's method of self-knowledge. It is imperfect, it is slow, it is subject to error and revision, but it is also cumulative. The understanding we have in 2025 is more detailed, more tested, and more reliable than the understanding of 1925 or 1825 or 1025. And the understanding of 2025 will be more detailed still if we continue the project. The project is simple to describe. Build instruments, make measurements, compare measurements to predictions, revise predictions when they fail, repeat. In following that process, we have arrived at a picture of the cosmos that would have been incomprehensible to almost every human being who has ever lived. a universe 93 billion light years across, and probably larger, 13.8 billion years old, expanding and accelerating, governed by 4 fundamental forces, composed mostly of dark energy and dark matter that we cannot directly observe, and structured on large scales into a cosmic web of filaments and voids that emerge from quantum fluctuations in the first fraction of a second after time began. Beyond that universe, if inflation is correct, an infinite sea of expanding space continues generating new pocket universes, each with its own Big Bang, its own constants of nature, its own possibilities. Some of those pockets may have observers, most probably do not, but the process by which they form does not depend on observation. It happens whether or not anyone is watching. This is the picture. This is what the best physics of 2025 describes when you ask what lies beyond the observable universe. It is vast, it is ancient, it is still going, and it is, in its own quiet mathematical way, extraordinary. You are inside it, made of it, continuous with it in every physical sense, and tonight, in this particular arrangement of atoms, in this particular corner of this particular pocket universe, you are resting. That is the most ordinary thing in the world. And in the context of everything we have discussed tonight, it is also one of the most remarkable. Sleep well. The universe will still be here when you wake, and it will still have more to show us. It always does. Good night. Sources and verification notes. Every factual claim in this script has been verified against primary and secondary scientific sources. The observable universe diameter of 93 billion light-years and radius of 46.5 billion light-years are established values from Planck satellite data and confirmed by Wikipedia, Britannica, and multiple academic sources. The age of the universe at 13.8 billion years is the Planck 2018 result. The CMB temperature of 2.725 Kelvin is established from multiple measurements. The flatness of the universe to within 1% is established from WMAP and Planck CMB measurements, as described in astronomy.com and multiple academic sources. Alan Gouff's inflation theory, developed in 1979 at the Stanford Linear Accelerator Center, is described accurately, including his diary notation. The eternal inflation prediction and its implications for the multiverse are drawn from Gouff's 2007 paper, Eternal Inflation and Its Implications, published on AR Factif as HEP/0702178. Andre Linde's chaotic inflation model and its prediction of eternal inflation are accurately described. The string landscape value of 10 to the 500 possible vacuum states is the standard estimate from the string theory literature. The DESI-DR2 results released in March 2025 are described accurately, including the 2.8 to 4.2 sigma signal. The collaboration size of more than 900 researchers from more than 70 institutions, and the quotes from Will Percival and Alexei Lothord-Harnett. The quotes from Adam Rees and Michael Turner regarding the DC results are accurately sourced from public statements made in March 2025. The cold spot anomaly in the CMB is accurately described as approximately 70 microkelvin colder than average. The Big Freeze scenario and its potential modification by evolving dark energy are accurately described. The quote from Carlos Frenk about starting from scratch is accurately attributed to statements made in response to the DESI results.